Hey, Math 105 students, I'm going to show you a few things. It's me, Gary Parker, and we're going to play around with spreadsheets. So, I have a spreadsheet here where I'm playing around with some of the finance problems. Let's load this up a touch. Go over a few of these. So, number one in the exercises is about regular compound interest, as is number two. Number three is a flipped problem in that it gives you the future value and you have to come up with a present value. So that's a pretty straightforward application of the compound interest formula. And so here I want to take my initial balance and then I multiply. If you think back to the previous chapter, this right here is my growth multiplier. And then the years times the periods per year gives me the total number of periods. So I just want to repeatedly multiply by the growth multiplier. Pretty straightforward application of simple interest into compound interest. Next one's pretty similar. Again, starting with my balance, I have my growth multiplier here. And then I have to raise that to the power of the number of times I apply it, 12 times per year for 5 years. Not too bad. This one reverses it, and to reverse that, basically we undo a multiplication with a division. And so here I'm going to divide by the growth multiplier over time. All right, so now we're going to get to the fun stuff. So here I have a couple of versions of calculating an annuity. So this is a savings annuity. In a savings annuity, we send the same amount of money to the bank each month, say, could be each year, as I have in the next problem, over a certain amount of years for some annual percentage rate. And so here I have the formula written out in relative cell references. And the formula, remember, is in the book. And so we're just trying to apply that book formula. Now, most spreadsheets have formulas to do the same kind of thing. So the book formula, which is listed here with cell references, can also be found by applying the future value formula. And here, with the future value formula, I have to be sure to enter the initial balance as a negative number for it to come up with a positive answer. The reason is we're putting money in over time to make a sum, and that's not a good reason. Anyway, if we don't do that, we get a negative value here. So the future value formula, FV, is for periodic payments into an account. And it will tell us what that total amount is later. Some of the payments here are pretty straightforward. I just take my payment times the number of times per year and the number of years, and a quick subtraction here will tell me how much interest I'm going to earn in addition to my payments. Same idea here in number 5. I'm just applying that to a payment of $3,000 over paid each year for 30 years. So just a different compounding period. You get interest once a year and the payment comes once a year. Now you can do fixed payments and collect interest over a different time, but the formula is much more complicated, so we're not going to take a look at that one. But that's a possibility too. The formula is easy if the payment period and the compounding period match. All right. Now, what I want to do here is something a little bit different than we do in the book. I want to explore this recursively. So I'm going to back up to problem number 4 and show you a spreadsheet here that analyzes this month by month. So here I have the same thing I had before, calculation of the future value of $400 paid in each month for 25 years at 2% per year. And so applying the formula in the book, we can come up with this future value here. I want to look at it in terms of month by month. What's happening in the bank? So I'm putting $400 in each month. And to make that formula happen, I just say look in cell A2. And since I'm going to fill this formula down, I put a $ in front of the 2 to make it an absolute reference. So that way, if I take it and use the magic fill button, it's always going to look in cell A2. If I didn't have the $ in front of the 2, when I filled it down, the computer would give itself the freedom to change the 2 to a 3, and then a 4, then a 5, and that's just going to give me nonsense. So whenever we make a formula with relative cell references, we have to ask ourselves, are we going to move this formula somewhere else by filling or copy and pasting? If so, then we need to decide when to put $ for absolute references and when to leave it alone. So the payment is an absolute reference. I always want to grab it from that cell. Here I am making the payment at the end of each month, and so I don't get any interest in the first month. It's after that I start collecting interest. So let's see how I start collecting interest. Well, I'm going to take my previous balance, which has been sitting there between the end of month 1 and the end of month 2, and I want to multiply that by, and this is a simple interest calculation, very straightforward. Simple interest is the principal times the rate times the time, and the time is 1/12 of a year, so I'm just dividing by 12 at the end here, using a cell reference. Now, something to keep in mind, when I calculate the interest, the balance is changing each month, so that stays without $, that's relative. The APR and the periods per year, that's always in row 2, and so I had to put a $ to fix that to calculate the interest, and that's ready to fill down. As far as the balance goes, the balance is just my previous balance plus my new payment plus the interest based on the old balance. Really simple sum. Once I have those formulas, an absolute reference for the payment, a combination of relative and absolute references to get the interest, and a combination of just relative references to find the new balance, I'm ready to fill it down. Now, computer remember, or spreadsheet, I should say, when you give it a pattern of 2 numbers and highlight them, again, highlighting is clicking in the middle, dragging and letting go, and then I grab the fill button and I fill it down, will generate linear patterns, so 1, 2, 3, 4. I'm doing this a slightly different way. Here I'm saying take the previous period reference and add 1 to it. So that's going to generate the numbers 1, 2, 3. So now I have a set of formulas in row 6 here, the second row of my table, and I'm ready to fill it down. So let me just drag that. Now here I have 12 times 25, which is going to be, I think, 300 rows. And so I'm going to fill it down. And I'm just going to fill it over the stuff that's here. So that's going to go down quite a ways. And you can see I already have data here. And I'm just going to overfill it. And it's going to recalculate. I'm going to get the same number I had before. So what the spreadsheet tells me is that if I pay $400 a month and my interest calculation is based on that 2% over once each 12 months, that I'll have $155,528.45. Scrolling back up to the top, I just put a reference to that last cell in D304 here. And I'm just confirming that I get the same thing as the book formula. Book formula is this relatively complicated combination of growth rates and growth multipliers over a given amount of periods. Alternatively, simple interest formula and some additions with relative and absolute references allow me to generate a spreadsheet that calculates month by month what's happening with my account, which is pretty darn cool. So I'll share this with the class later, this whole spreadsheet. It's a very nice thing to be able to do. So that's a savings annuity. So I replicated that same spreadsheet in the next one here. This one was where we were just paying once a year and collecting 8% interest once a year. And so we can see what happens over 30 years. So just a lot fewer cells because I'm only doing it once a year. But I can see here that the final formula I have just with simple interest and sums is the same as this wild calculation using the savings annuity formula from the book. Pretty cool stuff. All right, let's take a look at one more, and that'll be enough for today. The last one here is where I've been saving money for a long time, and I have $500,000 in an account. Now I'm ready to retire, and I want to start collecting that money. And so I wanted to calculate how much money I can take each month so that over 25 years, collecting money once a month at 8%, again, 8% is what the lending or the saving institution is going to pay me for keeping this money in there. Now I'm drawing down the money. That's a little bit of a complication because some saving institutions give you an interest rate based on maybe how much time you're going to keep the money in there, but often how much money you have in the account. And I'm drawing this account down. And so I applied the inverse, really, of the formula that we used earlier to calculate the amount of money I would pay out each year. And so all of these formulas are related. And so here's this formula here, which again is the book formula, but applied with relative cell references. So let's take a look at what the month-by-month breakdown of this is going to be. So I have that in my last tab here. So in this case, I just replicated that top part here, the formula I'm using to calculate the monthly payment. And okay, this is a payout annuity as opposed to a savings annuity. It's a slightly different formula. Now here, relatively simple, I'm starting off with $500,000 and I'm using this payment. Now I calculated the payment a little bit different. There's a payment function in Excel which comes up with the same answer as the book formula. It doesn't necessarily, again, show how the number was calculated. It just says to make this calculation, we need a periodic rate, we need the number of periods that's elapsing, and then we need to know what the initial value is. And here I made that a negative so that I get a positive value showing here because we're withdrawing. And that negative sign makes sense. Some of the other formulas in Excel, because I'm using the formula in a strange context, the negative is kind of weird, but it's what I had to do to make it work. So here, let's take a look at how the balance is calculated. Notice how much simpler this is, because I don't have to worry about the interest. I could have another column here showing the interest that's being accrued each month, but I have it just living inside. So here, what I'm doing is taking my balance and applying the growth multiplier to it. Now remember, a growth multiplier takes your growth rate, the periodic rate, and adds 100% to it. Because then if I multiply by that, I know my new amount. But I'm also drawing my account down by a fixed amount each month. And according to the book formula here, or the spreadsheet's PMT function, if I draw this down at $3,859.08 each month, after 12 years at 12 times a year, sorry, 25 years at 12 times a year, I should get a zero balance. And so I did a similar trick here where I'm just saying take the previous period, add 1 to it. Here I have, notice everything is an absolute reference here because I need the present value, the APR, periods per year, and the number of years to calculate the payment. And I want that same payment to come down each year. Now, instead of using the payment function each year, I could have just referenced the number above here, but I just wanted to demonstrate again, there's another way to do it. Often spreadsheets have built-in functions to do these things. So I'm just going to fill this set down, and 12 times a year, 25 years, that should give me 300 months. So we're just going to fill that down for 300 months. And what we should find is we get a zero balance at the end. And bang, there it is. I finally drawn my account down to zero. And so the point was to find a payment such that as my account collects interest each month, I withdraw a fixed amount each month so that in the end I get exactly zero and I always get the same amount each month. So that's how a lot of retirement funds work. And that's called a payout annuity. So I will share this spreadsheet also. And that's it for now. So have a good day, week, month, year, do good math, and stay in touch. Let's see, and hello world, goodbye, have a nice time.